So let's look at another proof of one of the limit laws using the definition of a limit. Right, so in this case, we want to prove the following theorem. And so we want to prove that if the limit of f as x tends to a is L, the limit of g as x tends to a is m, and f of x is less than or equal g of x for all x, then the limit values L and m's must satisfy this inequality. So then L must be less than m. Right? So what we're proving is if f is less than g, then the limit of f is less than or equal to the limit of g. Okay. Now this proof is interesting because it uses an important method of proof in mathematics, and that is proof by contradiction. Right. And how that works is we assume that the conclusion isn't true. Right, so the conclusion here is that. Right, so we're assuming that the conclusion isn't true. Right? And then we show that if the conclusion isn't true, right, then the assumptions can't be true either. In other words, then we get a contradiction. Right? So what are we assuming? Right, so we're assuming that the conclusion isn't true. Right, so we're assuming that L is in fact bigger than M. Right? Not equal, strict inequality. L is bigger than M. Well, what happens when L is bigger than M? Well, then in this case, and if we let epsilon be, say, L minus M over 2, then this is going to be bigger than 0. Okay. And now we see that because limit as x tends to a, f of x is L, right? That means that we can find, say, delta 0 bigger than 0, so that if absolute value x minus a is between 0 and delta 0, then absolute value f of x minus L is less than L minus M over 2. Right, so this is just the definition of a limit for this particular value of epsilon. Right. Now, writing down this inequality is the same as saying that minus L minus M over 2 is less than f of x minus L is less than L minus M over 2. Right? So if we just look at this side of the inequality, we see that f of x is bigger than L minus M over 2. And if you do the calculation, you'll see that this is the same as L plus M over 2. Let's call that A. Right. So if absolute value of x minus a is between 0 and delta 0, then f of x is bigger than L plus M over 2. Right. But we also know that the limit as x tends to a of g of x is m. Right? So then again, by the definition of a limit, so there is, say, delta 1 bigger than 0, so that if x minus a in absolute value is between 0 and delta 1, then absolute value g of x minus m is less than L minus m over 2. Right. So that means, in particular, g of x minus m is less than L minus m over 2, which gives you g of x less than L plus m over 2. And we'll call that inequality B. Right. So now, if we let delta be the minimum of delta 0 and delta 1, then if absolute value x minus a is less than delta, then, well, by a, right, because delta is less than delta 0, and by b, because delta is less than delta 1, we get f of x bigger than L plus m over 2, and that's bigger than g of x. Right, so we see that if x, absolute value x minus a is between 0 and delta, then f of x is bigger than g of x. Right, we see that's a contradiction, because we assumed that f of x is less than or equal to g of x, right, for all x. Right. And this is a contradiction. Right, we can't have f being bigger than g and f being less than or equal to g at the same time. Right, so this assumption we made at the beginning can't be right, because it leads to a contradiction. Right, so in fact the assumption mustn't be true. Right, so if L can't be bigger than m, then it must be less than or equal to m. Right. And that's a nice example of a proof by contradiction.